Today's lesson is on the application of exponential and logarithmic models. And our book uses some different equations than what I'm used to. So what I'm going to do today is I'm just going to give you some basic formulas that just make things a little easier in my opinion. So you definitely have to have your calculator handy and learn how to store your answers in your calculator, because it makes it very easy to use in order to solve these formulas. So the first thing we need to talk about is radioactive decay and what it is. It's definitely something that is pertinent in our lives, your lives. When you get an X-ray, that's radiation. We use radiation treatments for cancer. And, well, what this is then is a radioactive material loses itself over time. And we call that half-life. Typically, we talk about an element having a half-life is if it is radioactive. And the formula we use is A of T equals A sub 0, which we call A naught, times e to the kt. Now k is our decay rate, A naught is our initial amount, and t is our time. Now we're going to use the exact same formula for the exponential growth model. I use n instead of a, but it doesn't really matter. All the values are the same thing. N naught is the initial amount. K is the growth rate, and t is time. So nothing really changes there. Basically use the same formulas. Our final, and then I crossed out 3 and 4 because our book uses those, but I'm really not a fan of those, so I'm just going to use these two plus Newton's law of cooling. Now don't be alarmed at this mu. This is Greek letter mu. Looks like an M. You can say M, I don't really care. But this is how I learned it, and this is how I teach it. Mu of T, that means the temperature now, is equal to the surrounding temperature, capital T, plus mu naught, which is the initial temperature of whatever it is we're talking about, minus the surrounding temperature, usually the room, times e to the kt. So mu naught is the initial temperature of the object. So if you think about it this way, you have a hot cup of coffee, you put it down, and all of a sudden, over time, it cools off to room temperature. Well, that's what this formula predicts, how fast and what temperature and things like that. So K is our cooling or heating constant, and T is our time. So we're going to start here with example 1, and it says let me preface all this with saying this. You're usually going to find K. That's usually the first thing we have to use in order to solve an equation. We got to know the growth rate or the decay rate. That's really what's important. So if you look at example 1, it says under ideal conditions, a certain bacteria population doubles every 3 hours. Well, if we start with 1,000 bacteria, we want to know what the formula is. Well, we don't know the constant, the growth rate. So we got to find K. That's usually what we're going to have to do anyway. Well, we started with 1,000, but then it says it doubles every 3 hours. So we'll have 2,000, right, after 3 hours. So I'm just using this formula, e to the kt. The initial amount's 1,000. We have 2,000 after 3 hours. We got to find K. Okay, now this is where it's important we know how to use our calculator and algebra, obviously. The first thing we would do is divide by 1,000, and if I do that, I just get 2 equals e to the 3k. Then we're going to get rid of e by taking the natural log, which is really nice because that leaves us with natural log of 2 equals 3k, And we can find k by dividing by 3. So k is exactly the natural log of 2 over 3. That is our growth rate. So if you type that in, natural log of 2 divided by 3, it's about 0.231. But we don't want to be all about. We want exact, okay? So now take that number that you just typed in your calculator and go find the button that says STO arrow, press it, and it should say answer, and then you should have an arrow. And we're going to store this in alpha K, which is alpha open parentheses. And you should end up with this on your screen. Press enter, and you'll get this full number again. That K then is registered in your calculator. Now, why would we want to do that? Well, number one, we're not rounding. And number two, we can just press the button K on our calculator, and we have the number. So if I want to know how many bacteria I have after 15 hours, then it's simply plug it in. We started with 1,000. We know K, and we know time is 15. So we type in 1,000 second E to the 15 alpha K, or K15, whatever, it doesn't matter. And we would have 32,000 bacteria. So by simply storing our K in our calculator, it certainly cuts down our time. Now, C is a little different. We're looking for the time. Same formula. We want to know how long it'll take to reach 100,000 bacteria. Okay? So it's the same formula, and K, the growth constant, is still the same. The growth rate's the same. So now we have to find T. Well, the first thing I'm going to do is divide by 1,000. So I'm going to knock some zeros off. So you have 100 equals e to the kt. Now we're going to do the same thing every time. Look what I did up here. Natural log, those cancel. I have the natural log of 100 equals kt. I'm looking for t. I'm going to divide by k. There's my answer. Natural log of 100 divided by alpha k, and it would take approximately 19.93 hours in order to reach 100,000 bacteria. So that skill of finding K and then putting it in your calculator shows up to be quite handy. If we go to example 2, and be sure you pause this anytime you're hesitant to move on. Just pause it and look at what's going on and replay it if you have to. Example 2, we're already given K. Check it out. We know K, so we don't have to find K. That's rare. Usually we do. It says, according to the U.S. Census Bureau, the world population from 1995 to 2003 can be modeled by the exponential equation that T is between 5 and 13. Now, T equals 5 represents 1995, and P is in millions. According to this model, when will the world population reach 7.1 billion? Well, this is in millions, okay? 5,340 million is 5.34 billion. So I'm going to use billion here instead of million because it's easier to work with, and we need to find T. Well, there you go. We got everything we need. The first step, divide by 5.34. So second step, take the natural log of both sides. That eliminates the E. Third step, divide that by 0.012922. And there's T. Now we don't have to store anything. Just do the arithmetic that it says to do. And it would take 22 years. Make sure you're checking this. Do it along with me. To get to 7.1 billion if we use this model beginning in 1995. Now here's the crazy thing. That would be 2017, right? 22 plus 1995. Well, we looked up the world population in class to see what it was in 2017, and alarmingly, it was 500 million more than that. It was 7.6 billion. So this model had to be changed rather quickly because the world's population is continuing to grow at a rapid rate. Okay, example 3. Now, we have a typo there. Empire's population has grown exponentially from 326 people in 1952 to 12,044 people in 2012. What is its annual growth rate? Okay, well, we got to find K because it's asking for it. Well, we still use this problem or this equation. It's the same equation every time. N or A, it doesn't matter. We had 12,044 people, but we started with 326, and that was 60 years, correct? 1952 to 2012. So in 60 years, we went from 326 people to 12,044. So now I'm going to solve for K by dividing by 326, natural log of all that. That eliminates the E, divide by 60, and there is K. So now this is definitely one we want to store. We don't want to mess with this thing. 12,044, the natural log of, divided by 326, divided by 60, and then we're going to store it in alpha K. And mine is stored. I got a growth rate of about 6%. Okay, just about. But I'm going to store that. Now, if the growth rate remains constant, in what year will the population reach 25,000? Well, that's what we know that it's 25,000. If we started with 326th, we want to know how long it will take. So we're looking for T. So if it seems redundant, it is. It seems like we're doing the same algebra every time, isn't it? Natural log, divide by K, there's our T. So the natural log at 25,000 divided by 326, close parentheses, divided by alpha K, it will take about 72.14 years to get to 25,000 people, starting in, 1952. All right? So again, it just seems like we're repeating the same thing, right? Which is great, because that helps us learn it. Now, this one's kind of cool, really cool actually. This gets into half-lives and radioactivity. And this talks about the Chernobyl incident, and this was quite fast. It was crazy. I remember it very well growing up. And you basically, you can go there, but it's at your own risk. It's still radioactive even to this day. So it says find a model. Okay, find a model, which means find an equation. Well, this is where we use that A if you want, or you could still use N, it doesn't matter. But the big key is we have to find K, the decay rate. Now we know that the half-life of plutonium is 24,360 years. That means if we had 10 pounds today, 24,360 years from today, we'll have 5 pounds. That's a long time, okay? So what we want to know is what's the decay rate then? Well, if you have 10 pounds, but you're going to have 5, right? Because the half-life, we got to find K if the time is 24,360. So we go ahead and do the math. We'll divide it by 10. And then we do the natural log. That's 0.5, by the way, and then natural log there. And then we would divide that by 24,360. So K is natural log of 0.5 divided by 24,360. So again, this is definitely one you want to store because the decay rate is going to be tiny, 24,360. Store alpha K, there we go. Okay, I'm going to leave it like this. So then it goes, how much plutonium is still present today? Well, if this happened in 1986, that was, let's see, 14 plus 21, 35 years ago. So we want to know today, if we had 10 pounds, what would we have today? How much is still there? Well, that's one where you can type straight in. 10e to the 35 alpha k. 9.99 pounds still remains. Makes perfect sense. Look at the half-life, right? Now C asks, when will it be 8 pounds? Okay, so we do the same thing, but now we're looking for T. So 8 equals 10e to the kt. So of course you divide by 10, natural log, divided by k, right? That gets me T. So we're going to take the natural log of 8/10 divided by alpha k, and it's going to take 7,842.2 years before it gets down to 8 pounds. So the key in all of these, guys, is to find K. Find K. All right, last one. And this is our Newton's law of cooling or heating. It doesn't matter which it is. It doesn't matter. You can still do it. The difference is K is positive or negative, the heating constant or cooling constant. So we have a cup of coffee, has a temperature of 200 degrees, okay? That is mu naught. That's initial temperature. Placed in a room that has a temperature of 70, that's room temperature, that's capital T. We need to find K. I mean, basically, that's what it boils down to. Well, we're given some extra information here. After 10 minutes, it's at 150. So that's where we're going to jump off to. 150 equals 70, because that's our room temperature. Initial temperature minus room temperature, e to the k T. Well, you said 10 minutes was T, right? It was 150 degrees. And now you just do the algebra just like you did before. Subtract 70. You get this. Divide by 130, right? I don't show all the work because I shouldn't have to at this point of your math career. Natural log of both sides, and then divided by 10. So K is equal to the natural log of 8/13 divided by 10. So again, this is another good one to store. Divided by 10, store alpha K. All right, so there's K. Now it says find the temperature of the coffee after 15 minutes. So we want to find the temperature after 15 minutes. 200 minus 70, remember, is 130. E to the 15K. So we can type this straight in. That's 130. So 70 plus 130 E to the 15 alpha K, and that temperature would be about 132.8 degrees Fahrenheit. After 15 minutes, that coffee would be. Pretty slick, isn't it? Now, next question. When would it be 100? Well, all we do is do the same thing, but I want to know T now. So we would do the math, subtract 70, divide by 130, zeros cancel, that's gone. Natural log of 3/13, natural log of that side, divided by K. So T would be the natural log of 3/13 divided by alpha K. about 30.2 minutes, and that coffee will be cooled to 100 degrees. Now, there are two more formulas I want you to write down today. Compound interest and continuous compounding. I think you know both. I'm just making sure you get those written down because they will be part of your assignment today. So on your assignment, while I'm thinking about it, make sure that you look at closely let's see, number 4. Oops, I don't know how that happened. Number 4, Chiefs, right? Number 4, you got to find K on A. So that's what you're going to do for A. Just find K, period, and then use it. Number 5, K is given, so no big deal. Number 6, you must find K. So number 6, find K. That's the number one thing. Number 7, find K. That's your growth constant or your decay constant. And on number 8, there's a mistake. K should equal negative 0.1947. So make sure you change that to a minus sign. And then on number 9, guess what? You got to find K. If you do all that,